picking up where we left off yesterday. We've got this example. So we were talking yesterday about the factor theorem, the remainder theorem, how we generate zeros, or how we identify maybe zeros. So this question is going to be the first one in which we actually learn or get insight, I guess, to the procedure for factoring polynomials that we don't already know how to factor, meaning fourth degree, or most fourth degrees, most third degrees, all fifth degrees, all sixth degrees. We do have some ability with some fourth degrees. You guys remember the ones that were like of quadratic form. We have the ability with some cubics if they all have an x in them, or if there's four terms, we can factor by grouping. So some of those we have some shortcuts to factoring, but collectively as a group, all cubics and all quartics and all quintics and everything beyond that, we don't have a very large scale procedure to factor. This is going to be that, okay? So what I want to do here, first of all, is there's a typo. This -1 should actually be a -2. But I want to do synthetic division here, okay? So I'm going to take the original P of X coefficients of 3, -8, -14, 31, and 6. All right, it just says show that the given values of C are zeros, okay? So I'm going to put a -2 out here, and I'm going to just demonstrate that that does end up giving me a 0, which what that means to me, that if that is a 0, then x plus 2 would be a factor of my polynomial. Does that make sense? Meaning that x plus 2 would divide the polynomial, or we could say that 3x to the fourth minus 8x cubed minus 14x squared plus 31x plus 6 is divisible by x plus 2. Okay? So let's go ahead and do this synthetic division. We'll bring down to 3. And then we start multiplying, right? So -2 times 3 gives us -6. Add that gives me -14. Multiply gives me 28. So positive 14 now. -28 is a positive 3, and then a -6, right? So does that show that -2 is a 0? Okay, so that is the visual, that's the algebraic work to demonstrate that x plus 2 is a factor of the original P of X. X plus 2 divides that original polynomial, okay? Now, remember what polynomials are. Polynomials are, and this is just any algebraic phrase, is a representation of some number when you know what x is, okay? So let's say if I choose x to be 1, this rule here, if I choose x to be 1, this rule takes that 1 and transforms it into another value, right? Okay, so let's just come to the side here real quick and make an argument. If I take the number, let's say 42, and I ask you, is 42 divisible by 2 and 3? Okay, you've got a couple options. You can say, oh, well, 42 divided by 2 gives me 21, right? And 42 divided by 3 gives you 14, right? And because those were whole numbers, that meets our definition of divisible, right? We talked yesterday, if we say something is divisible, it means the result is a whole number, no decimal portions, okay? And And what we mean by that is, division is repetitive subtraction. It means that if I take 42 and subtract 2 away from it until I get down to 0, that's going to happen 21 times. If I take 42 and subtract 3 away from it 14 times, that will get me to 0. Does that make sense? It's kind of the way that we view division. Okay, so that would be it. Yes, it does. But could I also do this? Could I say, is 42 divisible by 2 and 3 by doing it this way? 42 divided by 2 is 21, and then 21 divided by 3 gives me 7. And because that 7 is a whole number, then it shows that 42 was divisible by 2 and 3, right? Or you can do it the other way around. You go 42 divided by 3 is equal to 14, and then 14 divided by 2 still gives me 7. Okay? Now the logic of that is because the prime factorization of 42 is 2 times 3 times 7. If that's my prime factorization, then I know automatically, yes, these are divisible by 2. And I can also then say, automatically, that they are divisible by 3, right? Okay, so if you divide by 2 first, these go away, and you're left with 3 times 7. The question is, well, is that then divisible by 3? Yes, it is. Okay, so my argument, the reason I'm saying this is we could come back to this, and you could see if 3 divides this polynomial by putting a 3 in the box. Don't write this down. You put a 3 in the box, and you can write the original -3, -8, -14, 31, and 6. And you can put that in the box, and you can bring the 3 down, put your 9 there, get your 1, get your 3, -11, -33, -2, -6, and it gives you a 0. And that would be validation that yes, 3 is a 0. Would you guys agree with that? Okay. What happens there, though, is that this last row of information, what is that row right there? If this was x to the 4th right there, correct? The final row is now x to the 3rd, right? And it's the same thing for what I did in red. Okay? So if I want to continue factoring this, I have to have then strategies to factor that yellow row of 3x to the 3rd minus 14x squared plus 14x plus 3. And we don't have very good strategies to do that. Okay? And actually what we're doing now would be that strategy. So, because of this argument that I could take 42 and say it's divisible by 2 and 3 by checking 42 divided by 2, get that result, and then divide that by 3, or reverse the order, do 3 first and then divide by 2. And because they both give me this whole number of 7 back, that means over here, because this just represents a number, I can do the same thing here. So maybe this was analogous to like the 21, okay? So I took 42 divided by 3 and get 21. So now I'll take the 21 and divide it by whatever I need to. Does that make sense? So I'm going to start with this yellow line now. And you can rewrite it if you want. I usually just put a box right there, and I'm going to put the 3 in that box. And now I'm just going to do a synthetic division with that. So I'm going to bring my 3 down. Multiply gives 9. That gives me -5. Gives me -15. -1, and then we get our 0. Does that make sense? It's still a 0 that we got over there in red, but look at this line now. This line, this 3, -5, -1 line would never have been generated if I always go back up to the original P of X coefficients. Okay? And why is that 3, -5, -1 line important to us? Why do we want that to generate? Think about this. You said this was x to the 4th, right? Somebody told me that this was x to the 3rd. When I take x to the fourth divided by a linear factor, it depreciates to x to the third. We just took x to the third and divided it by another linear factor. So what's that going to depreciate down here to? X squared. And then this would be x to the first, right? So if these are 0, so if this was a 0 right there, that tells us that number right there was the actual 0, right? Okay. So if that was the 0, then x minus that is a factor. Okay. If you remember, we said if we're calling that term c, if c is a 0, then x minus c is a factor. Okay. So x minus -2 would be x plus 2, right? Okay. Now, because that number is a 0, remainder of 0, that tells us this was a 0 for our function. So x minus that would be a factor. And then our other factor that we currently have here would be the 3x squared minus 5x minus 1 equals, oh, not 0, p of x. Okay, so did that allow us to take our original polynomial and break it down a little bit? Okay, and we can, I mean, there's all kinds of calculators out there, guys, that allow you to quickly do this. GeoGebra has this built into it. I'm just going to take the x plus 2, x minus 3. And I think I can actually type it in here. I go expand x plus 2, x minus 3, times then 3x squared minus 5x minus 1. And if I expand it, that's the command for it to distribute. Does that get me back to what I started with? It's exactly the same thing we started with, right? Okay. So it gives me, that was my input. Okay. It expanded it. Okay. So I know right now that this is the alternative form of this. Okay. Now, something we're going to learn is that every single polynomial of any degree, can be factored to a product of linear terms. Would you agree that that's linear? And that's linear, right? So it can be factored to a product of linear terms and quadratic terms. Okay. That's on the real number line, a real number system. Okay. If we want to go a little bit further and bring in complex numbers like square root of negative 1, which is I, we can make the argument, and we'll see this theorem written out later on, that every polynomial can be broken down to a product of linear factors. Right now, it's a product of linear factors and quadratic factors. Okay. However, this quadratic factor can go further. Okay, Sam?
If you don't have any value at the end, that doesn't have an x, like the plus 6 up there, if you didn't have anything and you're doing synthetic division, do you need to put a 0 in for it?
Yeah.
Okay.
Yep. So let's look at this. This is a quadratic. Do we have a way to factor that thing? Quadratic formula. Okay. Now, remember what the quadratic formula is going to do. The quadratic formula is going to give me my zeros. Okay. If we use the quadratic formula, which is x equals the opposite of b plus or minus square root of b squared minus 4ac over 2a, right? So let's run that thing through here with that set of a, b, and c. So we'll have 5 plus or minus, it's 25 minus 4 times a times c all over 2a. So that's going to give me 5 plus radical 37 over 6. And it's going to give me 5 minus radical 37 over 6. Okay. Those are my two x values. Does that make sense? I know those from previous discussions, previous content, that those are zeros. Those are x-intercepts, correct? Okay, so those are c values, much like this number right there was a c value, and much like that number right there was a c value, right? So if I want to find the factors for this, okay, we have the factor already of x plus 2. We had the factor of x minus 3. Now I'm going to have the factor with that being my c term. So I'm going to go x minus, and then it's just the safest thing to do is just to put that in parentheses. So I go 5 plus root 37 all over 6. And then we'll go x minus that c. So I'll put that in parentheses, 5 minus root 37 over 6. And that is what we call the complete factorization of our original polynomial. Now, there is one little caveat to this. If you were to multiply all that out, and this appeared when we did the quadratic formula here. If you were to multiply all this out, just look at the first terms. X times x times x times x would give you what? X to the fourth. What was our original polynomial? 3x to the fourth, right? We lost a factor of 3. Okay? We put that back in. Okay? Put it back in anywhere what? So you'll put it in that factor, put it in that factor. You'll put it there, put it there. You'll put it there, put it there. You'll put it there, put it there, right? My suggestion, don't put it inside any of the individual factors. Put it out front. Let it be your a term. Put it out front. And now you've got your polynomial. Okay? The one thing I think is important for us to understand, and we'll see this a couple different times, when I take a polynomial that has particular zeros, so let's do this, cancel. If I go like x minus 3, x plus 3, x minus 1, and let's go x plus 4, okay? Those are my zeros. If we look at, let me change fit this thing to the graph a little bit better. Okay, so we have that polynomial, right? If I put, just so we can see the order pairs easier, if I put a value out in front here, if I say a times that, okay, and I'm going to change this a, okay, would these be different rules, different p of x's or f of x's? That makes sense? But do they all have the same a, b, c, d? They have the same exact zeros, right? Okay, so if we were to look at the problem that we just had, the function that we just had, if I have, it was x plus 2, x minus 3, x minus 5 plus the square root of 37. That was divided by 6. And then x minus 5 minus square root of 37. That was divided by 6. All right, so if we have that thing, okay, or we have that thing, then times our 3, do they still both pass through the exact same x-intercepts? That makes sense? But our 3 that we lost through that quadratic formula needs to be present, okay? Because this purple one is indeed that original polynomial that we were interested in, right? Okay? So whenever we are provided zeros for a function, we need to usually be provided extra information sometimes so that we get a specific polynomial instead of general polynomial. So if I just give you what is a polynomial that has zeros of 2, 3, and 5, we could potentially in this class have 20 different answers that are all correct, right? Okay. So what I'll do is I'll say, give me a polynomial that has zeros 2, 3, and 5, but has a leading term that has a coefficient of 5, something like that. So now everybody's going to have the same result, and that's kind of what the next questions are going to get at. But right now, what we effectively did was took a fourth degree polynomial, which we had no understanding of how to factor prior to today's class, and we factored it, right? Okay. Now, what did they have to do for us in order for us to factor this? They had to give us 2 zeros. Okay. They have to give you enough zeros to where you can figure out what the quadratic is that works inside that polynomial. So they had, because this was fourth degree, they had to give me 2 zeros so that when I do the synthetic division, my resulting is a quadratic. If they give me fifth degree, they would have to give me 3 zeros so that when I do the synthetic division 3 times, my final line will be a quadratic. Does that make sense? Okay. So however many degrees your polynomial is right now, they have to give you that minus 2 zeros. Okay. And that, so you might be thinking, well, why are we even doing this? They got to do half the work for us, or most of the work for us. Okay, in regards to, they have to provide us extra insight that we wouldn't necessarily know to begin with. In the coming sections, we'll discuss on how they knew -2 and 3 were options. Does that make sense? Okay. So we'll get to the point where we can do all of this on our own. All right. So what we're talking about there with that example as well is, what is the safety net for factoring quadratics? What is the go-to tool that will always work when I factor a quadratic function? Okay. What we just did, and when we have the ability to find the initial zeros of -2 and 3 by ourselves, that will be the safety net. That will be the end-all, be-all technique that factors every single polynomial we could ever come across of any degree. Okay, so it's essentially that quadratic formula safety net for all polynomials. Does that make sense? And it even works for quadratics. But if you use this for a quadratic, I don't want to be mean, but it's kind of moronic. Okay, because you got faster techniques. Okay, because in the long run, this can be time consuming, especially when we have to find those initial zeros first. Okay, so now let's reverse the procedure a little bit. Okay, so doing these problems multi-directional, I think, helps us understand the concepts a little bit better. This says find a polynomial of a specified degree that has the given zeros. Okay, so this is going to be using the idea of what we talked about in regards to that factor theorem yesterday. Factor theorem said if C is a 0, then X minus C is a factor, right? Okay, so coming back down here, if these are zeros, if -1, 1, 3, and 5 are zeros, then what is the factor that comes from that -1? X plus 1. Okay, it's always X minus C, which C is always the 0. Okay, so X minus -1 turns into X plus 1. What's going to be the next one? X minus 1, and then X minus 3, and then X minus 5, right? Now, when we write our polynomial, so that polynomial, if we were to graph that polynomial will go through those 4 zeros, those 4 x-intercepts. But we usually don't like to write it that way. Okay, they want us to expand this. Okay, so when I expand this is just a practice of distributing. Okay, I call it distributing instead of foiling because foiling blows up when you are multiplying anything other than two binomials, right? Okay. But FOIL is just, if I don't know if you guys, if this was ever explained to you this way, if I'm foiling that, first times first would be that times that, right? A times M. Outside times outside would be that times that, right? Did I just distribute A to the second set of parentheses? And then O would be those two, right? Or sorry, I would be those two. And then L would be those two. Did I just distribute B to both things over here? So foiling is just a mnemonic phrase for telling you to distribute everything in one set of parentheses to everything in the other set of parentheses. All right, and that I think is, I hate FOIL. I hate that phrase because people then get down to like a trinomial times a binomial or trinomial times a trinomial, and they don't know what to do because they don't have a word for it, okay? But if we understand that it's just distributing, then we can extend that to any type of multiplication. So what would be the, be intelligent about foiling here. I don't want to foil 4 times. And especially, some of our questions are going to have, 6, 7, 8 different factors. You do not want to be sitting there and wasting your time foiling and multiplying if there are tools that can be used to help you. And one of those tools is to look at that one and that one. Why would I choose those two to multiply together first? Okay, so when I multiply those, O and I cancel out, right? Okay, if I were to use that FOIL technique. So, anybody remember what those types of terms are called? Binomials, when it generates a difference of squares, right? Okay. But if they're the same terms, but they differ by the sign that's connecting them. Remember what that's called? It starts with a C. You do it in English, the verbs. Conjugates, okay? So those are conjugates. And conjugates, by definition, mean that their O and I's cancel out. So x times x gives me x squared. And then 1 times -1 gives me that. So I don't even have to worry about O and I, right? Okay? If I didn't see that pair of conjugates, and I took x plus 1 for some reason multiplied by x minus 3, I'm going to have 3 terms. You'll get to the same answer, but you're going to be spending more time on this problem than your neighbor. Now, these two are what I have to. Good. Okay. And at this point, now FOIL doesn't work because FOIL only works for binomial times binomial, but you're going to take x squared and you're going to distribute to all 3 parts over here. So it's going to give you x to the 4th minus 8x to the 3rd plus 15x squared, right? Minus x squared, multiply my -1 times everything over here, so minus x squared plus 9x minus 15. And then I'm going to combine like terms. And that then, when I combine like terms, is my polynomial P of x that has degree 4, right? Seeing that, and it was generated by using those zeros. If you were to graph that, it's going to go through those zeros. It's going to be the same exact thing if you were to graph the original red one up there. I have x plus 1 times x minus 1 times x minus 3 times x minus 5. Okay? But there are a lot of other polynomials that go through those zeros as well. This is the only one that goes through those zeros and has a y. What would the y-intercept of this one be? -15. That's the only one of all the infinite different polynomials that have those zeros that would go through -15 as on the y-axis. So if you had so the way this question is phrased, it just says find a polynomial. So if you wrote 2x to the fourth minus 16x to the third plus 28x squared plus 18x minus 30, you have a polynomial that has those zeros. Does that make sense? Okay. So there's a lot of different options there for that one. Okay, if they don't specify. So that's where it gets kind of messy with WebAssign, with handwritten tests. If I just say write a polynomial, I could have potentially 40 different questions that I have to, and answers that I have to judge, right? So what I'll do is something like part B here. Yes, Andrew?
Shouldn't that be plus 8x?
Huh?
Shouldn't that be plus 8x instead of plus 9x?
Here?
Yeah,
Yeah, why'd you write 9?
I don't know, I'm sorry.
Yes. Thank you. But the idea that we could have infinite number of answers that are all true, or all correct, generates the need for questions like this, part B. So it's find a polynomial of degree 4 with those zeros, but a coefficient of a cubic term that is 4. So initially we're going to address this right there. That's all we're going to do. We're going to do the exact same thing we did in the last problem. Okay? So doing this as we did in the last problem, what would be one of my factors? X plus 2. Okay, what is the factor that's going to give me there? Just X. Okay. If I just have just X, I like to put it out front. And then we have X minus 1 and X minus 3. Now in this one, I don't know that there is a best way of choosing which ones to group. There's no conjugates here, right? So I'm just going to plug away. I'm going to multiply those two out. So it gives me X squared plus 2X. And I'll multiply these two out. So it gives me X squared minus 4X plus 3. Is that okay with everyone? Then I'm going to just distribute. So X squared times X squared is X to the fourth. X squared times negative 4X is negative 4X cubed. X squared times 3 is 3X squared. 2X times X squared is 2X cubed. 2X times negative 4X is negative 8X squared. And then 2X times 6, or times 3 is 6X. And there should be some like terms we can combine there, right? When you start combining like terms, because obviously you get a lot of terms, and this is only a 4th degree. Once you have 5th degree, 6th degree, that kind of stuff, this list gets very long. What I like to do is I write one down and then I cross it off. Make sure I don't use it again. And then I go look at negative 4X to third or the other X to thirds. So that one and that one, right? Combine those gives me negative 2X cubed. X squared, so it's that one and that one. So I get negative 5X squared and then plus 6X. Okay, it's a good strategy to cross those off when you're simplifying. We did it last period. Last period I missed one. Okay, but when I was crossing things off, I was able to pick up on it. Does that make sense? Okay, so that is a polynomial. If we look at this, if we graph that, X to the fourth so X to the fourth minus 2X third minus 5X squared plus 6X, okay? Or if we would have just written it as, GeoGebra can graph it as X times X plus 2, X minus 1, X minus 3, okay? I like to graph them both simultaneously because it then indicates to me when I toggle off the colors that I do have two equal representations of the same thing, right? Okay. Now there are those are the zeros. If we we look at the roots here, so those are the zeros that we were provided in the problem, okay? But is my cubic term the positive 4 that they were asking for? Is that a positive 4 right now? No, okay? So what we need to realize is that there is an infinite number. There is an infinite number of polynomials, okay? So this red one here is the polynomial that we have written down in our notes, okay, that we have expanded. But this gray one is all of the other polynomials that have the same zeros, right? Does that make sense? Okay. So when I write it like this, I wrote it as A times that. That is a generic polynomial. It's representing all of the polynomials that have those zeros, okay? When I specify that A, let's do it this way. Okay, so I want that A to be something that generates this number here to be a positive 4. Right now it is a negative 4. So what's it got to become? Negative 2. Okay, so I basically what we're trying to do here is figure out what does the A need to be? Well, A needs to be to meet the criteria that number right there needs to be a 4. Well, how do I turn negative 2 into a 4? So I multiply by negative 2, right? So I need to multiply everything by negative 2. So it's going to be turning negative 2x to the 4th plus 4x cubed plus 10x squared minus 12x. And now that is the one polynomial that has those zeros, and it's the only one in which the cubic term is a positive 4. So there we went from essentially having an infinite number of polynomials that can be expressed to now only having one, because I gave you that extra condition, extra criteria. Does that kind of make sense on how to do that? Okay. And they could do that to any term. They could say, "I'll make the squared term be, negative 15 or something like that." So if I want the squared term to be negative 15, I multiply everything by 3, correct? They might say, "Oh no, this one doesn't have a constant term." If it had a constant term, maybe they ask us. You see in the next example we'll do tomorrow, it says make the constant term 6. Okay? So we'll talk about how we can do that. That one gets a little bit messier because some of the zeros are. I think I got some. Look at that. There's a irrational zero there. Okay? The thought though is the practice is if we can start with zeros and get to this. Okay, think about what you guys did in Algebra 1. First thing that you learned in Algebra 1 was how to multiply, how to FOIL, right? And then after you learn how to FOIL, the next couple weeks you learn how to factor, correct? So that's this idea here. Okay, essentially what we're doing is FOILing longer things, more than 2 binomials. But then hopefully that procedure allows us to eventually factor. Because when you're in 3rd grade and you started to learn how to divide, what did you do first before you learned how to divide? You learned how to multiply first, because they tie together. Okay? Keep working on that 3-3 assignment in WebAssign. We should have everything in 3-3 wrapped up by the end of tomorrow. And then 3-4. 3-4 will be. Might have to find it. But 3-4 is going to be the section that tells us how to start with zeros. Okay, how? Because the author right now has to give us a starting point. After 3-4, we will generate that starting point on our own.